Hi, and welcome back to Neil's Not So Boring World of Chemistry. If this is your first time joining us, we're happy to have you here, and I hope you'll consider subscribing to the channel. In this edition, we're learning about Le Chatelier's principle. Specifically, how does heat affect a reaction that's at equilibrium? Now, I would suggest that before you proceed, you refamiliarize yourself with a couple key terms. Firstly, what does Le Chatelier's principle state? Second, what does it mean if a reaction is said to be at equilibrium? And lastly, the term enthalpy, which we'll be using throughout today's video. Feel free to pause here and catch up with those ideas. And when you come back and join me, we'll be ready to learn about this topic together.
What's up, everybody? Welcome to Neil's Not So Boring World of Chemistry. Let's go into the lab and take a deeper look.
So it's really hard to have a meaningful discussion about chemical reactions without considering energy. We know there are lots of chemical reactions and processes that actually release energy, and it's often in the forms of heat or light. Let's take a look at this burning match. We would say that this reaction is exothermic. Exo means outside or external. So there was energy stored within the match itself that is being lost. It's leaving the match and going into the surroundings. So in contrast to our last idea, we have other reactions and processes that actually take energy in instead of releasing or losing it. We call those endothermic reactions. Endo meaning within or absorbing. Take, for example, these melting ice cubes. In order for this water to go from solid to liquid, it has to actually take energy in and absorb it from the surroundings. So how can we predict whether a reaction will be exo or endothermic when we're only given a chemical equation? In order to understand that, we're going to talk a little bit about enthalpy. And the definition of enthalpy is the internal energy of a chemical system. You can also see that it's represented by a capital italicized H. So basically, enthalpy is the amount of energy stored within a reaction like the one before you. Now, in Le Chatelier's principal problems, after your chemical equation, you're generally going to see this symbol, which is a delta H. Now, in the physical sciences, or science in general, I should say, delta represents a change. Also, the capital italicized H, as we just discussed, is enthalpy. So this value, delta H, is basically telling us how did the internal energy of these chemical reactants and products change as the process occurred. Now you'll see that there's a value given, and it's a negative number. Negative means loss. So remember how the match, while it was burning, lost some of the energy stored in the match to its surroundings? Well, this reaction is doing the same thing. Specifically, it's losing 824 kilojoules per mole. Whenever we see a negative value for our delta H, we know we have an exothermic reaction. Basically, it's losing energy to the surroundings. And therefore, we can think of the products not just being in terms of the chemical products, but also heat. Heat was produced and is a product. Now, in the case of this chemical reaction, the decomposition of ammonium nitrate, we see that the delta H value is a positive number. What does this mean? Well, this means you have to add or input 28 kilojoules per mole of energy in order to get this decomposition reaction to happen. Whenever we see a positive value for a delta H or change in enthalpy, we know we have an endothermic reaction or process. And that means we can consider heat as a reactant. So in problems around Le Chatelier's principle, we know that we're going to be asked what happens when we disrupt a reaction that's at equilibrium. You can see here we've gone back to our iron oxide reaction, And we're going to assume that it's at equilibrium. You can see I'm using the double-sided arrow to tell us that the rate of the forward reaction and the rate of the reverse reaction are the same. Now, it's also important to remember that because the delta H, or a change in enthalpy, is negative for this reaction, it's losing energy to the surroundings. It's exothermic. And that's why I've added the heat symbol as a product. You're going to have to remember to do that, as chemical equations will not generally have heat included. Okay, so let's say we disrupt this equilibrium state by adding some heat. In other words, we're going to increase the temperature of the reaction. Well, adding heat when heat is a product would be no different than, let's say, increasing the concentration of our iron oxide. And in that case, what the reaction is going to want to do to regain equilibrium is use up whatever there's extra of, in this case, heat, and therefore make more of the reactants. So we would say that if we add some heat, if we increase the temperature, this is going to consume products and form reactants. Now we can also represent that by changing our arrow. You don't have to do this in your answer, but it's useful as a conceptual tool so that the arrow pointing towards the reactants is a little bit larger or more bold. Now again, because the reaction is going to shift in this direction, we would expect to see this concentration go up, this concentration go up, while the concentration of the iron oxide would go down, and we're going to be using up some of that extra heat that we added as well. Now, of course, there's another way to disrupt this, right? Let's take all of our props away, and let's consider what would happen if we instead took our reaction that's at equilibrium and we removed heat. So maybe we put it in an ice bath or something, and we're actually going to be decreasing the temperature in this instance. Now again, remember, heat is a product. So now, whereas in the last example we were increasing a product, now by removing heat we're taking it away. And therefore the reaction is going to shift equilibrium, and it's going to try to remedy that by favoring the products, by replacing that which was taken away. So we would say it's going to consume reactants and form more of our products. So we would expect the concentration of the iron oxide to go up. Also, some of that heat that was removed will be replaced. And the concentration of our two reactants, the iron and the oxygen gas, well, they're going to decrease in response to this disruption. Okay, so now let's disrupt our endothermic reaction. Remember, it's endothermic because the delta H is a positive value. So heat is absorbed, and that's why I've placed it on the side with the reactant. Okay, so in this scenario, what would happen if we added heat or increased the temperature? Well, again, this means that we're going to be disrupting the equilibrium state by adding too many things on this side. It would be the same as increasing the concentration of our ammonium nitrate compound. So in response to that, the reaction is going to try to reestablish equilibrium by using up those reactants, whether it be extra heat, as we have in this case, or extra reactant. So it's going to consume reactants and form more products. So let's switch our arrow so that it favors the product side. And we'll also use these arrows to show that the amount of our heat and our reactant are going to go down as they're consumed, and the amount of our ammonium ion and nitrate ion, they're going to increase. So equilibrium will be reestablished when this reaction consumes these reactants and produces more of the products. And I want to advise everybody, it's really best to use this language, consuming reactants, forming products. We don't want to use directional terms, such as the reaction shifts to the right or to the left. Okay, so the other stress that comes up in these sorts of questions is, of course, the removal of heat or a decrease in temperature. So in this situation, what's going to be happening is we're going to be taking away one of our reactants, right? Because again, in endothermic reactions, heat is on the reactant side. So if we remove some of this, equilibrium will shift so as to replace it. So we would expect a favoring of the reactant side in this scenario. In other words, to regain equilibrium, the reaction is going to consume some of the products to form more of the reactants. So we're going to see the amount of heat hopefully go up to replace the heat that was removed, but that means the other reactant, the ammonium nitrate, will have to go up as well. And we would expect to see the concentration of our two products, the ammonium ion and the nitrate ion, decrease. Okay, let's check for comprehension and do some practice problems together. Solving problems like the ones covered in this video can be done confidently by following 3 easy steps. In step 1, you should determine whether the reaction is exo or endothermic by looking at the delta H value. A negative number tells you that it's exothermic, while a positive number means it's endothermic. Next, I would write the word heat on either the right or left side of the equation. If we found our reaction to be exothermic from step 1, we want to write the word heat on the right side, as if it's a product. On the other hand, if it's an endothermic reaction, we write the word heat as a reactant on the left side. Next, we're going to evaluate the stress. There's really 2 types. Heat can either be added or taken away. If heat is added to the reaction, we know it's then going to favor the side that doesn't have the word heat. On the other hand, if the reaction is cooled or if heat is taken away, the reaction will favor the side that does have the word heat. Here's a tip for answering open-ended questions. Avoid the terms shifts right or shifts left. Instead, talk about what's happening to the reactants and products. Okay, here's your opportunity to test your knowledge. The reaction given is found to be at equilibrium. Which of the following will occur when the reaction is cooled? Please pause the video and think about your answer, and then continue watching to see the solution. The answer is D. When the reaction is cooled, the concentration of O2 will decrease. This is because the change in enthalpy is positive and we have an endothermic reaction. So we would write the word heat on the left side as if it's a reactant. Cooling is a way of removing heat, so we would be decreasing a reactant. The reaction will attempt to replace that which was removed, so it consumes products so as to make more of the reactants. O2 is a product, and therefore its concentration will decrease. Thanks so much for supporting the channel. Please follow me on Instagram to get updated every time a new video is posted.